Hi everyone, welcome back. My name is Jazmin Rodriguez and I will be your teacher for this lesson. I hope y'all are excited as I am. Now class, I do have a question for you. Why wasn't the Angle able to get a bank loan? Well, because his parents wouldn't co-sign for him. Well, class, today we are on Module 4, Chapter 11, and we will be covering transformations, symmetries, and tilings. How exciting! Now let's go ahead and get started. For problem number 1, Ephraim and Devontae were asked to reflect this image on the left over a horizontal line that runs through the center of our square. When they did, they came up with this figure right here. Now we want to know what type of rigid motion did they use to create this image from this one right here. Well, they used rotational symmetry to get this figure. We know this because we can see that they rotated the image 180 degrees. Now, what they were supposed to do was reflect the figure over the horizontal line through the center of a square. So this right here is going to be our horizontal line. Now, let's reflect this across this line. All right, and then this means that it's going to produce an inverted image. So for example, there's our trapezoid and it's an inverted version. Then we do our square, which remains the same. And then we have our two triangles. So this one, we went ahead and inverted it, flipped it over. So when you flip it, it turns this way. When you flip this one, it looks that way. And this is how our figure is supposed to look. All right, now for problem number 2, we are giving these shapes right here, and they want us to determine which shapes have one line of symmetry, but no rotational symmetry. So let's go ahead, and I'm gonna tell you it's gonna be the half moon or circle, the triangle, and then the side triangle. Now let's take a look at each one and see why these fit into our criteria. So first we have the half moon here, and let's go ahead and draw our line of symmetry. So a line of symmetry, in order for this, is going to be that this half looks the same as on the other half. So it's a reflection. One half has to look like the other half in order for this to have symmetry. So this one has a line of symmetry. Now, in order to determine whether it has rotational symmetry, the figure has to look like itself whenever you turn it 180 degrees or less. So you can rotate it 45 degrees, you can rotate it 90 degrees, or 180. And if the image looks the exact same, then it has rotational symmetry. If you have to do a 360 degree turn, then it has no rotational symmetry because it has to be 180 degrees or less. So let's turn our figure at 90 degrees. And that's how it looks. Now, does this look like our original image? It does not. Now let's go ahead and rotate it another 90 degrees for a total of 180 degrees. Does that look like our original image? I don't think so. So therefore, this image has one line of symmetry, but no rotational symmetry. Now let's look at our second figure, and we'll go ahead and draw our line of symmetry for this one as well. And now we want to know, does one half look like the other half? It does. Another way that you can look at this is, what if you folded this in half? If both sides match, then they're symmetrical. If we folded this in half, as you can see, it is symmetrical. So this one has a line of symmetry. Now let's go ahead and see if it has rotational symmetry. So we'll flip it 90 degrees. Does this image look like the one on our left here? I don't think so. Now let's go ahead and rotate it another 90 degrees. Does this image look like this one? It does not. That means it has no rotational symmetry. And our last figure, we have a triangle again. And we'll go ahead and draw our line of symmetry. One half matches the other half, so it has a line of symmetry. Now let's move on to rotational symmetry. And we'll turn this 90 degrees. And that's how it'll look. That does not look like our original figure. And let's do 180 degrees. Does that look like our original figure? It does not. So once again, that has no rotational symmetry. Okay, and for the second part, we are once again given this set of shapes, and they want us to determine which of these shapes have rotational symmetry, but no reflection symmetry. So we are going to go ahead and tell you that these are going to be the shapes. Now let's look at this figure, first of all, and let's go ahead and see if it has reflection symmetry. So we'll go ahead and draw our vertical line, and then does this top match the bottom? Is this a reflection of the bottom part, or the top part, excuse me? It is not. Now let's go ahead and try one more line of symmetry and see if it works. Does this side look like this side? It does not. That means that this image has no reflection symmetry. Now let's go ahead and see if it has rotational symmetry. We'll flip the image 90 degrees. Does this image look like this one? It does not. Now let's go ahead and give it one more try. Now, does this image look like this one? Ah, it does. So that means that this has rotational symmetry. So this is why this fits into the criteria of having no reflection symmetry, but rotational symmetry. All right, and let's look at our last figure here. And once again, let's determine if this has reflection symmetry. And we'll go ahead and start with our vertical line. Now, does this half of our image look like this half? It does not. So far, it has no reflection symmetry. Now, let's go ahead and do a horizontal line. Does this half look like the top half? It does not. So therefore, this has no lines of symmetry, and if it has no lines of symmetry, it means it will not have any reflection symmetry as well. Now let's look at rotational symmetry. Let's flip it 90 degrees. Does this image look like the original? It does not. Now let's go ahead and flip it another 90 degrees. All right, does this image look like the original image? It does. All right. Now, for the third part of this, it wants us to, based off of these shapes, it wants us to determine which one has one line of symmetry and rotational symmetry. So we've already covered all of these shapes and determined either or. So let's just review those real quick. We have that the half moon had no rotational symmetry. This one had rotational symmetry, or this one did have a line of symmetry. This one did as well, and it had rotational. This one had no rotational. This one had no rotational symmetry as well. This one did have a line of symmetry. This one had no reflection symmetry. And this one had no reflection symmetry. Now let's go ahead and look at each one of these individually since we have narrowed them down. So let's start with our rectangle. Oh, it has one line of symmetry, right? And we already determined that it has rotational symmetry. But wait, this one has two lines of symmetry. And what did our problem ask? It said that it needed to have one line of symmetry and rotational symmetry. So therefore, our rectangle is not going to work. Now let's move on to our other figure. And we have a hexagon. And oh, it has a line of symmetry. Awesome. Well, it also has 2, 3, 4, 5, and 6. Once again, it's only supposed to have one line of symmetry, so our hexagon will not work as well. And let's look at our rhombus or diamond. Oh, it has a line of symmetry and rotational symmetry, but it actually has two lines of symmetry. So once again, our problem needed it to have just one line of symmetry and rotational symmetry. And although all of these do have one line, they actually have more. Therefore, this is not possible. All right, now for problem 3, we are giving a regular pentagon, a hexagon, and an octagon. And we have Miss Myra, who thinks that when she put these together, that they were going to form a vertex figure. A vertex figure is known as an arrangement of non-overlapping tiles that surround a common vertex. That means it is where the common vertex is where all of our shapes meet. So this is going to be the vertex. This is where all of our three different shapes, the pentagon, the hexagon, and the octagon, all meet. And we also know that they cannot be overlapping. So in order to determine whether Miss Myra is right or not, we need to find out the measures of each individual interior angle of each figure. And the measure of the interior angles combined that they meet at this vertex have to add up to 360 degrees. That is a requirement. If we want this to be a vertex figure, those central angles have to add up to exactly 360 degrees, not more and not less. So let's go ahead and start off with our first one. Well, first of all, to find the central angle, we have to use our interior angle formula. And we'll go ahead, and as y'all remember, we have already studied this, but I'll go ahead and give you that just so you don't have a hard time remembering. Our interior angle formula is n minus 2 times 180 divided by n. N is going to represent the number of sides of our shapes. So first, we'll start off with the pentagon, which has 5 sides. And once we solve it, we get that the interior angle is going to be 108 degrees for the pentagon. And then we'll go ahead and solve for our hexagon. Once again, it gives us that it has a 120 degree angle. And our octagon, which has 8 sides. And the angle is 135 degrees. So now that we have calculated all 3 of the angles, let's see if she is right. So we'll go ahead and add up all of these 3 angles, and if it adds up to 360 degrees, she will be correct. All right, so our total looks like it's 363 degrees, and we needed 360 degrees in order for this to be a vertex figure. So unfortunately, Miss Myra, you are not correct. These 3 shapes put together do not form a vertex figure. Now, what can we do to show Miss Myra what she could do to make a vertex figure? Well, first, she's going to have to change these shapes because those put together will not work. So let's experiment. Let's do a dodecagon who has 12 sides. And we'll do a hexagon which has 6 sides. And a square that has 4 sides. So let's try these out. And we have already, and this is what it'll look like whenever we put those together. And we went ahead and already determined the interior angle since we have already discussed how to do that. And we get that the dodecagon has a 150 degree angle, hexagon has a 120 degree angle, and the square has 90 degree angle. And when we added those up together, it was 360 degrees. So Myra, this is an actual representation of a vertex figure. We're so smart. All right, now let's look at problem number 4. And we are given this figure. And what it wants us to do is it wants us to prove that triangle QPT is congruent to triangle SPT. Now, how are we going to do that? Well, first of all, let's remember what congruent means. It means that they are equal to. So that means that we have to prove that those 2 triangles are going to be equal to each other. And I think that we are going to be able to prove this through the SSS property, which is side, 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 which states that if 3 sides of one triangle are equal to 3 sides of another triangle, then they are congruent. And as we can see, they have actually already given us a little bit of clue information. These lines right here mean that they are equal. So they have already pretty much told us that, hey, side PQ, or line segment PQ, is equal to line segment PS. And then they have also given us that these bottom ones are also congruent to each other. So they said QT is congruent to ST. And then we have this line PT, which is shared by both triangles. All right, and so therefore, we have just proved that triangle QPT is congruent to triangle SPT. We have one side, two sides, three sides that are equal to our other three sides of our figure. All right, now for part B, it wants us to determine that angle QPT is congruent to angle SPT. Now, we just finished determining that line segment PQ is congruent to line segment PS, correct? Okay, and then that means that these are going to have corresponding angles because those sides are congruent. So once again, that's how we know that these angles, angle QPT is congruent to SPT. All right, now for part C, we want to determine that triangle QPV is going to be congruent to triangle SPV. And I think we're going to do this through the SAS property, which is the side angle side. And in a side angle side, it states that two sides and an included angle of one triangle have to be congruent to two sides and another angle of the other triangle. And then that'll determine that those triangles are congruent. So we have already determined that line segment PQ is congruent to line segment PS, correct? Okay. And then also we determined that side QV is congruent to SV. And then right here, we can show we have a side, angle, side. Right here, side, angle, side. And that's how we know that triangle QPV and triangle SPV are congruent. And now let's go ahead and demonstrate that angle QVP is a right angle. So let's go ahead and look at this right here. We have QVP. And we see that this right here, this is our line, and these two angles are going to be adjacent to each other, which also means that they are supplementary. And whenever you have two angles that are supplementary, that means that together they add up to be 180 degrees. So if together they end up to be 180 degrees, we have two of them. So that means that half of it is 90 degrees. And a 90-degree angle is also known as a right angle. All right, now let's look at problem number 5. And it wants us to create a pentagon with the vertex points PENTA. And in order to do that, remember that a pentagon has 5 sides. So let's go ahead and build that with 5 sides. And we'll label our vertex point P, vertex E, vertex point N, T, and A. And then it also wants us to create an equilateral triangle with the vertex points PQR. And we know that a triangle has, or an equilateral triangle has 3 sides. So let's go ahead and build that. And we'll go ahead and label our vertex points as well. Awesome. And now it is asking us to inscribe the pentagon and the equilateral triangle into a circle with the center vertex of Q. And we'll go ahead and put that in there. There's our pentagon inscribed. And then our triangle. We're just putting those in there. And that's how our figure will look once we have put both of our figures in there. And now we want to know, what is the measure of angle NOQ? And so let's go ahead and put that together so that we're able to see it. NOQ. So we want to know the measure of this angle right here. We'll get ready because this one's going to be a little bit long. So let's go ahead. And first of all, let's go ahead and kind of take this apart to make it a little easier. And we'll take out our triangle. Okay, so we have angle POQ right here. And this right here we know is the central angle, is the center vertex point. And we formed the angle POQ. Now, if we were to connect every vertex point to the center of our center point here, we would create the central angles. So let's go ahead and do that. So as you can see, we've created 1, 2, and 3. And now we know that in order to calculate the degree of, or the measure of a central angle, you take 360 degrees and divide it by n. And n is going to represent our number of sides. So we have 3 sides. So that means that it's going to be 120 degrees. So each central angle, each one of these angles is going to represent 120 degrees. Now let's go ahead and look at our pentagon now. Now let's determine the central angles of the pentagon as well. And what we can do is you can either draw out each central angle like we did with the triangle, or by now we have discovered that the number of angles of the polygon will actually be equal to the number of sides. So we actually don't even have to draw it out anymore. Once we know how many number of sides there is, that equals the number of central angles as well. And right here we see that we have 5. So once again, we'll take our central angle formula, 360 degrees, and divide it by 5. And we get that each angle is going to be 72 degrees. Okay, now let's go back to our original figure, because now that we have determined this information, we can find out what the measure of angle NOQ is going to be. And we know that angle PON is going to be 144 degrees. And you're probably wondering, wait, how? But I thought it was 72 degrees. Well, you're correct, but let me show you. Each angle was 72 degrees. Now let's look at our angle that we're at, angle PON, right here. If you see, this is taking up 1, 2 angles, not just 1. It's taking up 2, so it's taking these 2. Therefore, you have to add 72 degrees 2 times. So it was kind of a trick question. You would think it was 72, but when you look at it, it is actually taking up 2 angles. So we know that angle PON is equal to 144 degrees, not just 72 degrees. And we already determined that our angle POQ, which is the central angle of our triangle here, is 120 degrees. And all we do now to find this angle, because remember, we're trying to find out what this angle is, you take the big angle, PON, and you subtract POQ, and that'll give us this right here. And when we do that, we do 144 degrees minus 120 degrees, and we get 24 degrees. Ooh, that was a long one. Fun stuff right there, though. We're almost there. Okay, now for problem 6, I have a story. So we have Miss Jenny here, that she's out on a walk, and she sees that there's a cliff ahead of her that is probably about a quarter of a mile from where she is. Jenny decides she's going to hold up a ruler 2 feet from her eyes, and then she notices that the top and the bottom points of the cliff marks 1.5 inches on this ruler that she's holding up. And so before Jenny continues on towards the cliff, she wants us to figure out how high is that cliff going to be. She's probably not going to go up the cliff if it's too high. So first of all, let's go ahead and take this and kind of, do a little figure to make it easier for you. There's Miss Jenny, and this is going to be our cliff, and we'll go ahead and label it because as you can see, it forms a triangle. And we'll go ahead and put all our information. There she is holding it 2 feet from her eyes. So if she's looking at it, this is at her eye level, 2 feet. And then she's holding the ruler that marks 1.5 inches on it. And we want to know the height. Okay, so first thing, let's look at this. We know that triangle CED right here is going to be congruent to triangle CAB, which is going to be our bigger triangle. And we know that angle C is congruent to itself right here. And we know that angle E is going to be congruent to angle A because they're similar triangles. And similar triangles are going to have congruent angles. And then angle D is going to be congruent to angle B. All right, and therefore also CE, line segment CE, is going to be congruent to line segment CA. And then CD is going to be congruent to CB. And then we have that ED is going to be congruent to AB, which is our height of the cliff. Okay, now let's go ahead and look at this right here. And look at our information. So first of all, in order to calculate the height of this, we need to go ahead and convert our inches into feet. Well, we know that there is 12 inches in a foot, correct? So then we take 1.5 inches, which is what was marked on the ruler, and we divide it by 12. And that gives us that 1.5 inches is the same thing as 0.125 feet. All right, and so now here what we're gonna do is excuse me, there it goes. We're gonna go ahead and set up a proportion. So we are given that 1 mile is equal to 55,280 feet. So the first thing that we have to do here is set up our 2 feet over the 5,280 feet and set it up equal to 0.125 feet, and we want to know the height. So what we're gonna do here on our proportion is do some cross multiplication, and we get that 5,280 feet times 0.125 feet is equal to 660 feet. And then we do 660 feet and divide it by the 2 feet. So we get 330 feet. So that means that H is 330 feet, correct? Well, not so fast. Remember that Miss Jenny was standing 1/4 of a mile next to it, not a whole mile, 1/4 of a mile. So that means that we need to take our 330 feet and divide it by 4 sides. And when we do that, we get that it is 82.50 feet. So that's going to be the height of our cliff. All right, class. Well, that is all that I have for y'all today. I hope that y'all enjoyed this lesson, and we'll see y'all next time. Thank you.